Good morning. I'll just wait for a couple of seconds that everyone joins till we have joiners. Okay. So, welcome everyone. Today we have an interesting topic and expert on the field to explain us what this topic is. We have Aydın Yağmur from EOS, and Aydın will present us in situ process monitoring technologies. Bruno, I'm trying to mute the incomings, but it doesn't work, by the way. If you can do something for it, I don't know. Okay,
I'm on it.
Yeah, okay. So basically, I will on screen the agenda of the webinar. We will have some questions on Slido before we start with the presentation. And then Aydın will make his presentation and we will have a Q&A session afterwards. So now I want to put on screen the questions. I mean, maybe I should go to the next slide for that. One moment, please. Yes, here it is. So if we can go to slido.com and enter this code 3263488, you will reach the questionnaire that we prepared to make a kind of, let's say, analysis of the profile of our audience. I've started all the three questions online. The first one is, from which country are you attending the webinar? The second question is, how experienced are you in AM? And the third question is, what is your expectation from the webinar in 1 or 2 words? So if you can answer these questions in a couple of minutes, I will put on screen the results that we can talk about. Okay, thank you. Now maybe I should give the words to Aydın a little bit, that he presents himself, what he does in EOS. Yes, Aydın, can you tell us about yourself and what you do in EOS? What's your role? Thank you. Yeah.
Thank you very much for organizing and giving me the opportunity to reach the audience. My name is Aydın Yağmur. I'm a metallurgist. I studied metallurgical and materials engineering in Ankara, in Turkey. And then I worked in the conventional industry, what we call today, from AM's perspective in Turkey for about 6 years. In my last job, I got introduced to additive manufacturing and EOS, trying to build some jet engine parts and aerospace parts. And then I came to Germany to study Master of Science in University of Stuttgart. And since 2017, I am a member of Additive Minds team at EOS Application and Consulting Division, and trying to help our customers on process-related topics, starting from raw materials, powder, process optimization, monitoring, and qualification.
Perfect, perfect. So I want to repeat once again for the newcomers, before we start the presentation by Aydın, we would like to have your kind of opinion or the profile of our audience in the webinar. On screen, you see the code for the Slido. There are 3 questions over there. If you go to slido.com and enter the code, you will see these questions. The first one is from which country are you attending the webinar? The second is how experienced are you in AM? And the third one is what is your expectation from the webinar in 1 or 2 words? I see the answers for the third questions. For the other ones, maybe you should, in the slide screen, please look at the left. You should see the other questions. If anyone can have a look, because I only see the answers for the last question. What is your expectation from the webinar in 1 or 2 words? But the other ones are also okay.
Yeah. Hello, Kenan. Oh, okay.
Yeah.
Now I see the next question. I didn't see it before. It didn't change. Thank you.
Okay. Okay. Thank you. Thank you. Now I do it. It looks like I can run only one question at a time. I was thinking that it's all 3 questions would be possible to choose. Anyway, now we're answering the question: how experienced are you in AM? I will give just a couple of minutes, and then I will go back to the first question about the country you're attending. So if everyone is able to input their level of expertise in AM, I will pass to the next question in a couple of seconds. Okay, so now I am going to the next question. Yes, we want to see the profile of our audience. Probably it's international, I believe that, but mainly from Europe, of course. So, yeah. And this is a good time that people are still joining. Now, I will give another minute for this question, and then I will put on screen the answers. Yeah, okay. Maybe we can start with the first question. Let me put it on screen. Yeah. And you see the results?
Not yet.
So, one moment, please. I should share the screen probably. Yeah, now do you see it, Aydın?
It's coming. Yes.
Okay. So, this is a short questionnaire or survey we make to realize the profile of our audience and their expectations, let's say. As I guessed, I mean, our main audience is coming from Europe, UK, Spain, Switzerland, Sweden, Czech Republic, but of course we have China, Turkey, South Africa, so all welcome. Welcome. As I expected, AM is really an international business.
Yes.
So I would
great to see.
I would like to, yeah, I would like to go to the second question. How experienced are you in AM? Well, it looks like our audience is really high level. We have strong experts following us. So thank you for joining and giving time for this webinar. So the last question is, what is your expectation from the webinar in 1 or 2 months? I think, yeah, the most important expectation is to learn more about in situ monitoring. So that's why we are here. So we will see that. So that's all for the Slido. Thank you for your answers. Now I would like to introduce you the 2 organizations, that is EMA and EOS, shortly, and then give the floor to Aydın. Yeah. Okay. Let's go back. So as I said, this is the agenda. So yes, let me introduce EPMA first. The European Powder Metallurgy Association is a non-profit organization built in 1989 with the key missions of promoting and developing the powder metallurgy technology in Europe. representing the industry in Europe and internationally, and developing a future for PM, powder metallurgy. Basically, we say that EPMA is what its members want it to be. About the EuroAM sectoral group, this is launched in May 2013 and open to companies, organizations, even individuals across the supply chain who are willing to become members of EPMA. And the EuroAM group has four main objectives. So the number one is increase awareness on AM technology, especially metal powder-based products. Number two, enable the benefits of joint actions like research programs, workshops, projects, benchmarking, statistics, etc., and improve the understanding of benefits of metal-based AM technology by end users, designers, engineers, and students as well. And finally, to assist the development of international standards for the AM sector. About EOS group, I would like to say a couple of words. EOS is headquartered in Krailing, Germany, and EOS is a global leader in industrial 3D printing technology. Just like EPMA, it's also founded in 1989, and the company specializes in providing innovative solutions for AM, including both metal and polymer 3D printing systems. EOS cutting-edge technology is widely used across various industries such as aerospace, automotive, medical, and consumer goods, enabling the production of complex and high-quality components. With a strong commitment to research and development, ES continues to drive advancements in 3D printing and offering unparalleled precision and efficiency to its clients worldwide. So that's all about our organizations. Now, maybe it's time to give the word to Aydın. So
Thank you, Kenan, for the
maybe
introduction.
yeah, I should maybe stop the sharing screen. Yeah, okay, I stopped. Yeah, I'm back. So I know it's a lot of words and things. Sorry for that, but this is good for the entire structure of the webinar. And yes, Aydın, you already put on screen the in situ process monitoring technologies topic. So the floor is yours. We will have your presentation, and at the end of the presentation, we will have a Q&A session from with our audience. Okay.
Okay.
The floor is yours.
Great. Thank you, Kenan, once more. And let's start our webinar. I would like to today give you some insights on the technology, what is the today's state-of-the-art technology on in-situ process monitoring technology, in-situ monitoring systems, applications, of course, the fun part, and the trends and what is coming in the future. So I think it is self-explaining in the picture on the right side. It is more or less what are the differences between the upper part and the lower part, and how can engineers optimize the part from the upper version to the lower version. You see also less supports, less overheating. So why you should attend, or why monitoring technologies are as of interest today? Because if you look at the recent literature, scientific literature, it is calculated that cost reduction of more than 10% is possible with implementing monitoring technologies. Also, we see a lot of papers, research that process optimization, increasing the performance of materials, products is possible with process optimization, which is also possible and more effective by utilizing monitoring technologies. Of course, for the sake of creating a stable and repeatable process, it is very useful to understand the process and make fine-tuning, finding an optimization of quality, performance, and of course, cost of production. And in serial production, monitoring technologies also enable that process is documented, recorded, and available for later research or investigations. and it helps companies quality assurance and process validations, which is some kind of emerging trend. And we have some projects, ongoing projects, which I will describe in some detail in the coming slides as future trends. As Kenan mentioned, we are a global company focusing on only additive manufacturing, and I am a member of Additive Minds, so application and consulting division of EOS. And we are more than 100 individuals and maybe more than hundreds of years of cumulative experience in additive manufacturing that we help our customers quickly and reliably implement this technology. As EOS, we are leader in additive manufacturing solutions, and we see that our solutions will be or is being a part of digital factories of future. And we also see that our technology will be a key pillar of responsible manufacturing, which I may describe in the slide in a little bit more detail. So we see different aspects of our impact to on the society. Very first one is contribution to sustainability with our technology, production with less waste, less energy consumption, and less carbon emissions is possible. And also the cost effectiveness of production and the final product are increasing. And one of my favorite application is, of course, medical. We see a good advancement in medical industry, especially in patient-specific solutions for improving people's life. And since the production times from design or from idea to physical part is being shortened, we see that market entry times are getting shorter and shorter. And as a result of all this, we see a potential for greater economic growth with enabling different startups coming into the market and advancing the technology. Let's look at some examples how we achieve this. For example, this is a nice example from our partner or Additive Drives. It's a copper and aluminum application, Harpen Stator prototyping, which is built with additive manufacturing, which has some advantages like no other processes are needed, no forming or no welding is needed, and also the performance of the product is increased with additive manufacturing. Another application or an example is propulsion components. This is an interesting story with Hypergenic company. This part was designed by an algorithm, not by an engineer. So some kind of automation of design is emerging. And with our technology, we showed that this can be manufactured. We built this part first on an EOS M404 4-laser machine with Inconel 718. And the part that you saw on the video was also built on an AMCM machine with copper. Last example in this section is a heat exchanger used for racing cars. And with our partner Conflux, this application was successfully implemented. And what are the advantages? I think it's also self-explaining that the highly complex structure was achieved. So the efficiency of the heat exchanger increased, and the dimensions and also the weight were reduced, so that at total there is a very good improvement of the heat exchanger, having an effect on the automotive side. So we see a good commitment and a good way forward of additive manufacturing for a sustainable future, that we decrease waste, we increase the speed from to market, and we also see that supply chains are getting optimized because decentralized production is possible with additive manufacturing. Also, production on time is also possible. So stock costs and resource consumption is also decreasing. After this introduction, I would like to start with the foundations of our technology, direct metal laser solidification. I was naming for the technology. General literature is also saying laser powder bed fusion technology. And I would like to start with the foundations of technology. This will be an answer why we need monitoring systems. Since the audience is very well experienced, I will go very shortly on how the technology works. So we have a CAD design mainly, and we create slices of the part, so layers. We need to get the layers, and each layer is exposed with laser and solidified layer by layer. And for each layer, of course, powder is recoated for the next layers. And then at the end, we have the three-dimensional final part. We go a little bit into details. So how laser and material or metals interact. We have a good start approximation using power density and corresponding behavior of metal. So if the power density is less than 0.1 megawatt per centimeter square, this is simply heating of the material. And if we increase the power density to 0.5 megawatt per square centimeter, then we observe conduction melting. And if we even go on increasing the density, power density, then we have so-called keyhole melting, which is the heart of our technology. If we go on increasing more or more the power density, we observe plasma melting, which is not desired for our technology because the created plasma interferes the laser and avoids laser material interaction, decreases the efficiency of the laser absorption, and causes quality problems. So our technology is relying on keyhole melting. There can be some questions. So in the image you see there are some byproducts coming from the melt pool. Why we do not use conduction melting, which is a more calm process? So there are different reasons. The very first reason is the productivity. And the second reason is with keyhole melting, due to the shape of the deep, narrow shape of the melt pool, we can get better interlayer cohesion. So the connection between the layers are better. And due to the narrow shape, the absorption of the laser beam is better. So laser efficiency is higher. That is why we rely on keyhole melting in our technology. Let's have a quick look on a video from this source that we can observe the formation of the keyhole during this dynamic process. Between the red dashed line and blue dashed line, what we see is the molten metal. And within the blue line, we see so-called keyhole melting. And in this area, we have a laser beam and metal vapor. And also this area can create so-called spatters, which I will give some more details in the coming slides. And if the process is not optimized or some interference, some problems occur, what will happen? If the laser energy is not absorbed by the material in the optimized way, we observe a formation of volume defects, so-called lack of fusion defects, which are very dangerous or damaging the material properties because of the shape with notches inside. Lack of vision defects are not desired, are not accepted in additive manufacturing. You see different visuals here, SEM picture, right top side, and also we see metallographic pictures, and we can also estimate the shape of the metal powder, raw material, which were not fully fused or melted. This is the why we call it lack of fusion. So this is what happens if the energy input is less than the optimum values. And if it is too much energy on the other side, then we see this stability of the keyhole and causing more sphere-like defects. Sometimes I see that these are called like keyholes, and keyhole is not desired. This is not exactly true. So keyhole defects, which is coming from the destabilization of the keyhole, are not desired. Keyhole itself, a stable keyhole, is the heart of our process. As I said shortly, the process can create different byproducts, including so-called spatters, so solidified particles or metallic particles that is spread along the powder bed, and they may have different sources. For example, the very first type is created on the from the keyhole directly due to the pressure difference, and they can create some kind of sphere-like spatters. The second type is coming from the melt pool, where the laser has just passed and having more irregular shape, or molten material just falling down on the existing powder, non-melted powder yet, which has also different or irregular shapes. So these are mostly non-desired, or at least this kind of byproducts should be under control. That means laser powder bed fusion process is highly dynamic, and when it is not optimized or when some problems occur during the process, the byproducts created can cause problems. And that is why we need monitoring systems to record, understand how the process is being optimized, and also to check to qualify the process is working as it is supposed to be. We understood the need for monitoring systems, and let's see how monitoring systems work, what kind of information they deliver to us, and how we can understand, for example, different process behavior like we see here in a design of experiment build that we apply different parameters. What is in-situ monitoring in additive manufacturing? First of all, I can recommend you further reading a good ASTM standard, which you will find the handouts that we will deliver after the webinar. So it's very good for further reading. In my own words, in-situ monitoring is recording the data during fabrication with different sensors. I will give some details about type of sensors, and also analyzing data during and after fabrication. So this is also an emerging topic that I will also give some details. We can analyze data, and nowadays we can also control our process, regulate our process during the process using the data from the monitoring systems. At EOS product portfolio, we have different grouping of sensors. The very first one is powder bed. So it is like a webcam taking pictures of the powder bed after recoating and after exposure, and gives engineers a chance to analyze most of the building problems or recoating problems. Then we have a melt pool system. It is a photodiode that collects the backscattered laser beam in visible spectrum and near infrared wavelength spectrum that give insights from the melt pool, as the name indicates. The next system is Eostate Exposure OT, which is a unique solution in the market, that it is a camera taking pictures of the whole build plate during the layer time and gives us a long exposure or long time information of the powder bed, not only during melting, but also after melting. So, and we can see the whole build plate with Eostate Exposure OT. Quality reports are all the rest sensors, for example, oxygen concentration, temperature or humidity, which is also very useful to document and to analyze the production. Let's have a deeper look. What kind of sensors get what kind of data? This is the very first one, melt pool monitoring. This is an addition to the optical pad, and it detects the intensity of the light. It is a photodiode. What does it mean? Photodiodes can record the intensity of a given wavelength, but they do not have location information. This information is taken from the scanner, and the images, which I will show in a few seconds, are created from the melt pool. So melt pool is getting information from the melt pool only. So you can analyze the stability of the laser exposure with melt pool. The second system is a camera, so it knows where the signal is coming from. No additional information is needed for the data, and it takes pictures during the layer time. So it takes pictures before, during, and after melting, and we can have a integrated image of the full build plate. A big difference between OT and melt pool is with melt pool, we can gather data only from where the laser is melting. So we cannot get data out of the parts that are being fabricated. But with OT, we can also get data from the surroundings, so the whole build plate. And last but not least, we have our powder bed camera, which is also very useful for buildability problems, recoating problems, to understand how the process behaved. I would like to shortly show a good feature of our powder bed camera, that we can watch or observe the process live with powder bed, which is not being recorded, but we record pictures after recoating and exposure. For melt pool, so as I said, it is focusing on the laser exposure area and getting the location information from the scanner and created this compound picture. So all this information that we see on the right side was recorded by the photodiode, and the location information from the scanner, we created this compound picture. And what we see here is, for example, in this area, an overheating caused by short vectors, and we see the behavior during melting. Let's look at the same part, but this time OT picture. OT records the data not only during melting, but also cooling down, also solidification until the layer is completed. So we have a different picture here. So we see that a bigger area was influenced in terms of overheating, and this was detected by OT. And as I said, we can also see the spatter behavior. What lies behind this? Let's have a repetition. This is the camera taking data, pictures, 10 pictures per second during the layer time, and getting information, not only backscattered, but also any kind of emission created on the powder bed. This is the interface, and if you are familiar with EOS software, they have similar backbone. So it is, I would say, very user-friendly interface that we can see the created images. It is the same software, the same interface for both OT, melt pool, and powder bed. So we can see the images. We can see the statistical summary of the part during the Z height, and we can see the indications. So anomalies detected during the build by OT software. Let's have a look at what kind of anomalies can be detected. For example, here you see with the red line the anomaly on the part which is coming from the laser flow interaction was detected by our OT. We have different detectors that can be optimized, and we can detect this area. This is documented. The intensity of this area is documented, and we can compare and evaluate the formation and the severity of the indication. Here is again an example of short vector induced overheating. These areas also can be detected. And for further analysis, for example, stability of a process, maybe dynamic properties, dynamic material properties of a process can be detected by using OT images. So we can see here 4 different parameters applied, and with some third-party software, we can even make numerical analysis of the spatters. We can count them. We can also analyze the mean value and even size of the spatters. Some examples, use cases. So if there are dirts or problems on the optical path that affects the laser beam, we can detect them easily with OT because we see anomalies which can also be automatically detected always on the same position. So this is a good indication that there is something wrong in the optical path and causing, like, avoiding proper or optimized laser material interaction, and should be solved. Another use case that our colleagues in APAC region has worked with a university, and we also have a white paper. What is the correlation of OT with CT? Because CT is widely used in industry, and can we replace CT scan, or can we reduce CT scan costs by applying OTs? The answer is yes. We have created a setup that is causing unpredictable random problems on the process, and we then compare the signal behavior of OT with the CT scan, and we have come up with a result that there's a very high correlation of OT signal to the CT signals, so that it is a good proof that OT can be used to decrease the qualification or quality control costs. Another use case of OT is smart fusion, which is a relatively new technology that we have released last year. This is mainly regulating the process on the fly using the data coming from the OT system. And it avoids any kind of inhomogeneity on the part that can cause overheating and different problems like excess amount of residual stress, deformation, recoating crash problems, or different material properties. For example, we have applied 3 different parameters here, and I would assume that after this introduction, it would not be very difficult for you to estimate which part or which dog bone tensile specimen was built with smart fusion. So you can see that here smart fusion avoided the overheating and assured the homogeneity throughout the Z height. Let's have a deeper look how it works. So in this example, we built an impeller. So you see the layer n-1, and in the layer n, we see a lot of new exposure areas are melted just above the powder bed. And what does this mean? The thermal conductivity of the powder bed is poor. So this caused a lot of excess amount of overheating. And if you ever build some parts on a machine, on an AM machine, you may estimate that in 5 to 10 layers, this overheating will agglomerate to a lot of thermal stresses, and you will see recorder contact and recorder crash. And with Smart Fusion, in the next layer, we regulate the energy input of the process so that in these areas, overheatings are reduced. And in the coming layers, it will stabilize even more. If you don't use Smart Fusion, you see that the overheating will agglomerate, and even the part itself, so already solidified areas, will start to overheat, which will cause deformations and recorder crash. So it is not possible with nominal processes to build such an impeller. Let's look at some applications, what we built with Smart Fusion. This is an automotive bracket from titanium 6-4 alloy that we have built with our M290 machine. So Smart Fusion is available for all EOS metal machines. This time we use M290. And by reducing this support amount, we decreased the cost per part 34% because there are less supports used, less material used, build time decreased, so efficiency of the machine increased, and also the post-processing effort was decreased by decreasing the support amount by 80%. Another application is bicycle footrest that we have built or made the project with Punkel, and the final customer was KTM. And we could build again this part from titanium 6-4 with very less amount of supports, reduced supports, which brought us to the value that 35% of the part costs were reduced. And also the supports are so weak that even by hand, the supports could be removed. So not only the amount of supports to be removed were reduced, but also the effort for the remaining supports were reduced with Smart Fusion. Another example is a fuel tank, again from titanium 6-4 on M304 4-laser machine, that we could build this tank without any internal support. So this is completely closed. You have the top, you see the top section of the part that could be built again with Smart Fusion without any internal supports, which would otherwise not possible to build this part, or even if you could build, you would not be able to remove the supports after the build. Last but not least, we have this huge impeller, which is about 28 kilograms from Inconel material built on M44. And we built the part with 96% less supports using Smart Fusion methodology or technology, so that the part can be built with much less support without any problems. So with Smart Fusion technology, we see good potential for to increase the productivity, decrease cost per part, energy consumption, and scrap rate. After seeing like state-of-the-art monitoring systems and applications, I would like to show some insights of what is coming next. One project that we are now working on is applying statistical process control for OT data and analyzing these for quality control purposes. So we build different parts, and we analyze the nominal or natural deviation of the process intensity, and we create statistical limits. And whenever a limit is overachieved, then this means a problem or anomaly in the process which should be analyzed. So what we foresee with this improvement that we are working on is bringing quality assurance to the process during the build, which will decrease the cost and enable penetration of additive manufacturing to more applications. So this analysis we are working on to automate this. So different jobs should be built for the database, and afterwards this statistical process control we're giving insights about the quality assurance of the serial production. Are there any deviation from job to job, and what kind of deviations could be the reason? For example, is it an overheating? Is it a problem on the recorder alignment? So it will give more deeper insights, which is not easy to recover or easy to understand by just looking at some graphics. So it is a good advanced statistical process application that we are now working on. And our colleagues in North America have two very interesting projects that is going on. The very first one is to reduce the qualification costs and time with implementing different sensors, including OT and multiple monitoring. So we will build the layout and we will correlate the results with the sensor data. And then we will start to decrease testing. And the aim is to decrease the testing around 50% for qualification purposes, replacing the testing step by step sensor data. Another very interesting project that we are now working on, or my colleagues are working mainly on North America with different research institutes and industrial partners, is to design a new geometry of sample that will give information not only for tension, but also compression and bending. So just building one dedicated geometry that you see here, we call it D design. It will be possible to use also AI and monitoring data to test one sample instead of 3 different samples. So in this project, number of samples to be built for qualification will be reduced by implementing monitoring data and correlation to the parts and also the geometry of the part. Last but not least, we have a developer network that third-party companies can reach to our APIs and create their own software products or their products. To mention, we are now working with Interspectral or 1000 Kelvin that they use EOS developer network to develop their own products. That's all from my side, and I would like to get your questions.
Thank you, Aydın. This was a long and very detailed presentation. I'm sure the audience will have some questions. So to pose your questions, you can either raise your hand or put it in the chat. Please do not hesitate to ask any question of yours. I can start maybe with the first question from my side. I always wonder the challenge in evacuating the powder in the very first structure you have shown as the heat exchanger. You know, it's in the powder bed and the inside is very complicated.
Mm-hmm.
So how do you succeed in, let's say, cleaning such parts, the interior, that there is no clogging with the leftover powder, etc.? Is there a certain solution of use for that?
We have partners that we are working with, and the very first step to solve this issue is, of course, optimizing the process so that the powder, not melted powder, will not be caked or baked like a cake, so that it is still flowable. It should be still flowable, and we are using some depowdering equipment which can be optimized based on the shape and the complexity of the powder. And we are also following the literature. There are now new test methods are being developed. So we are also following these to test and prove that the powders are free.
Okay, because as far as I see, this is one of the most important challenges for internally complicated parts to make a good cleaning in terms of functionality. Yeah.
That's true. So there are two pillars. First, using equipment to depowder the part, and also the testing and proofing that there are no powder left, or no powder left is maybe a little bit too optimistic, but acceptable levels.
Yeah, we have a question first from Paul, and then there's a raised hand. Let's start with the question from Larson Andre, then I will continue with Paul. So Larson, you can unmute yourself and pose your question. Yeah.
Yeah. Thank you for a good presentation. A question regarding the monitoring system. Is there any what you say, calibration that needs to be done for new material if EOS hasn't worked with that yet?
For monitoring purposes, for OT, it is material agnostic. But depending of the physical characteristics of the material, like is it high melting point refractory alloy or low alloy, there can be some filters changed on the camera. No further calibration is needed. For multiple systems, each material and each process, I mean the same material with different layer thicknesses, even should be calibrated with a job of 10 hours depending on the process. So process specific calibration is needed for melt pool.
Okay, thank you.
Thank you. There's a question from Paul Davies. I can read the question. Will in situ monitoring become even more critical when the build volume utilization is very high, often incorporating several different components?
I think, yeah, we can definitely say it will be more and more critical, and the potential like implementing this OT monitoring data and analysis to do qualification or quality system will bring even more potential, because the quality assurance costs for, let's say, non-regulated or low regulated industries are around 15%. For highly regulated industries like aerospace and medical, it can reach up to 50% of a part cost. So of course, monitoring systems will be very critical to reduce these costs and also creating reliability. So it will create data and a proof that the parts have the desired quality.
Thank you. Any other questions regarding in-situ monitoring? Yes, Akash. I see a raised hand from Akash.
Yeah, thanks a lot. Am I audible?
Yes.
Yes, we hear you.
Yeah, thanks a lot for this nice presentation. I have two questions. First one is from in situ monitoring. When you say you are able to detect different melting modes, for example, and we want to target keyhole, which is stable melting mode. And there is also a keyhole which can be unstable melting mode. So is the photodiode that is measuring the intensity of the laser able to differentiate between stable keyhole and unstable keyhole? This was my first question. And second question is more on in additive manufacturing, we have post processing as well, heat treatment, hipping. So in aerospace, we are used to doing hipping, where you go through parts and you close all the porosities that are generated during the process. So do we at all need in situ monitoring, given the fact that we will do the hipping afterwards? How does it differentiate when we are talking about cost of the part, just with respect to builds and post processing? I don't know if I was clear, but
okay, let me try to answer first, and if I cannot answer, you can elaborate a little bit more. So first question, can melt pool differentiate stable keyhole from unstable keyhole? At the end, these systems are not engineers, so they need intelligence or like engineering understanding of the process. And what they can tell to us, are there regions on a part that are behaving different than the others? These systems can tell this information to us. And then it is engineers' task to translate this information to a language. What does this mean? First of all, implementing of these systems start with collecting data and checking the correlation between, for example, porosity analysis or tensile test. This is the very first step. Without this, let's say, physical test at the very beginning or physical test data of the same part, these are more or less some colorful pictures. This is the, let's say, how the story starts. And if, and in most cases, we see the unstable process behavior is being recorded by monitoring systems. And what pity is, these systems are even more sensitive than the material itself. So the trick is to filter out false positive deviations in the signal and try to focus on real process deviations. So for this, we need some statistical data from conventional test methods. And in the white paper, maybe we can also share the white paper with the participants, Kenan. We show a benchmark, so how we did it with impellers that I showed. Could
Yeah,
I
why not,
answer?
if possible?
Yeah, could I answer your question a little bit?
Yes, that was clear for me. Yes. Thank
okay. Hipping. So where does hipping coming from? First of all, the hipping that is, I don't know your application. I'm not judging your application, but what I have seen from the market is, of course, it makes sense to start what was implemented for different manufacturing methods. And the hipping methods, hipping recipes are mostly from casting industry. For different part of material property, different origins of defects, and also the scales are different. So hipping is, yes, closing some porosities, but at the same time has a risk of deteriorating the mechanical properties. So this is maybe first remark from my side. And you should also be very confident about what HIP can do. So in some discussions, it is said that like just build with 5% porosity and then you can close them with hipping. I think this is a little bit wishful thinking. So in my opinion, best thing is to build as high quality as possible and then cure or even improve it with hipping. So the less porosity that you have after the process, also the better for hipping, because if you have a lot of porosity, then you may have shrinkage problems. Then you have to calculate the shrinkage and then some kind of start with different geometry so that you assume that it will shrink to the final geometry and so. So I would always tend to start with the best quality ever. And in this sense, monitoring systems will be a good helper.
Okay.
Thank you.
That's good for me. Thank you.
Thank you.
Okay.
Just Karen,
Raja.
just sorry if you don't mind.
Yes, hello,
Yeah.
hello, Raja. Hello, hello. Yeah, please,
Hi,
please
how
go
are
on.
you?
Yeah, hello.
Yeah, so my name is Raja Khan. So I'm from TWI Cambridge in UK. So just a couple of things. Hi. So first, just very quick comment, because my expertise in hipping and all these things as well. So we also recrystallize the material as well. That's another advantage during the HIP process to reduce the scatter band in the mechanical properties of laser powered bed fusion. You see those, and yeah, the rest I agree with you, what you have explained. So the less the porosity, of course, gas porosities we cannot close even during the HIP process, and surface connected pores as well. So yeah, just coming to now a couple of questions. We have EOS M290 machine. So just was wondering if is these like in situ monitoring devices, so we can you see just buy from you and attach to our system, or is it that simple to do? This is the first question.
It is depending on the SI number, but most of the M290s are capable with OT. And with Smart Vision, we have to check your SI number. So you can reach out to me offline, and we can check. But most of the machines, most of the machine park, it is possible.
Excellent. The second question is, you see, in situ monitoring is one thing. Now, is there like you already working on or doing some research where we can correct as well while we build? So while we monitor, we detect something is wrong, and then machine self like align and correct that defect while we're building. Is it possible? In the future?
It's a question. Maybe we need support from academia. So we need research support. So this is a mechanism that is described or hypothesized. There are hypotheses that this happens, but I also try to follow the literature. There is no, I would say, clear proof that this happens, or there is no clear description or data that how this healing occurs. It may occur because we see, as I said, we see a lot of like false positive signals from OT, but we don't see all of them are in defects. So this is an area which is not explored yet, and I think we need some support from universities or research institutes like you.
Yeah, definitely we can discuss on that one. So thank you.
Yeah, thank you very much. I think this is all for the questions, and we've come out of time. I see that some people are just joining probably because of difference of time zones. Sorry about the webinar is over, but don't worry. The recording will be available on EPMA's YouTube channel that you can later on watch. And if you want to pose any questions, please do not hesitate to contact me or either Aydın, because at the end of his presentation, he has given his credentials. I think that's all for today and for this webinar session. Thank you very much, Aydın, for this intensive presentation and nice details that even for the experts, it was good to learn. And we hope to see you once again, maybe other time in EPMA activities as well. So thank you very much for all joining, and I wish you all a great day and hope to see you soon in another EPMA activity. So see you.
Thank you very much. Bye.
Thank you.
Bye.
Bye-bye.
Thanks. Bye-bye. Bye.
Bye.